I'm an application engineer intern with the application engineering team, obviously at nTopology. Today, I'm gonna walk you through something that we haven't really covered in previous nTop lives, and that's pretty much modal analysis. And we're gonna use modal analysis in a way that can benefit you in terms of working with automotive and aerospace applications. More specifically, we'll talk about how we can optimize lattice structures and graph-based lattice structures in this video to dampen or damp external vibrations on these specific applications, such as automotive and aerospace applications. So let's go to the nTop platform screen. The first thing I really want to walk you through is when using our lattice workflows, try to thicken your lattice structure using this regular block, where like our most often used block, where we just take our lattice body, we infill it using like an external, like implicit body. We assign a unit type, our scaling, our rotation to our graph-based lattice structure, and so forth. And then we thicken it using the thicken body block or the thicken lattice block. And then we get all these like basically beams which are thickened to the thickness value which is set here. However, a more robust way of designing this is to actually go by thickening your lattice structure based on relative density. So what do I mean by that? Relative density is essentially the volume which is used by your lattice structure versus the volume of the actual like solid model. So if you were to take this lattice or this implicit body, this box here, and we were to infill it with a lattice structure, instead of thickening it, we can do it based on something called relative density. And what I did here was create a reusable workflow where I could take in a block which is specifying this relative density and specifying, in this case, a cylindric radius and a cylindric height, and thickening up my lattice structure based on this value of relative density. So let's try this. We'll just put in some values in this block. Let's put in a scale of, I guess, 2 millimeters. Rotation, let's add a bit of a different rotation. Relative density of, say, 0.2. Let's make it 0.4 so you guys can see the actual thing. Radius of 12.5 millimeters and a height of maybe 30 millimeters. We'll let that run, and you'll see that our lattice structure is essentially designed with this idea of relative density in mind, and we're not thickening the lattice structure based on the beam thicknesses. And I want to credit another colleague on my team, Ryan O'Hara. He created basically the workflow for this relative density block, which should output soon. And you'll be able to see sort of this idea of what it looks like. So it's basically the lattice is thickened based on this notion of relative density, and we're able to extract like these ideas such as like the strut diameters and just the overall thickness values of the lattice structure. But using relative density is a more robust way of doing it, and I'll show you why and how it really applies to this idea of damping external vibrations for your automotive and aerospace applications. So covering this, I want to point you to a paper which will help guide us in the study that I'm going to show you today. And this paper really talks about how we can use lattice structures to absorb sound and damp external, like damp vibrations. In this case, we can see like a Boeing or like just a regular aircraft and all the components which are affected by vibrations. I want to credit another person, Dr. Sharma from Wichita State University, for offering us to use this paper so we could actually get a basis to this problem which we're trying to solve. So you can see all these components which are affected by airframe noise. And if we scroll down a bit more, he talks about lattice structures, he talks about TPMS structures, but today we'll just sort of focus on this idea of graph-based latticing. And if we scroll down a bit more, he explores testing various gradings of the lattice structures. You can have like a sine wave, an exponential decay, um, a linear decay in terms of the in terms of increasing the relative density or increasing the relative density in numerous ways, as pointed out here in terms of relative density. And he basically sets up his absorption analysis. So he gets like test models and he chooses different surface types. In this case, we'll explore different lattices. He chooses different relative densities, different unit cell sizes, and angles to the pores that he's working with. And he's able to get sort of an idea of the sound absorption coefficients of each of these lattice structures. So he's able to use like this impedance tube setup in his lab and get different frequencies and associate that with different absorption coefficients for various lattice structures, for various angles, for various unit cell sizes and relative densities, as you can see here. So we're going to try to use nTop to build our processes so we can achieve a similar sort of setup as this. So let's look at this idea here of testing various gradients in terms of relative density. What I did in nTop was sort of create a workflow where we can use these lattice structures we have here, or create these lattice structures we have here, and use modal analysis to our benefit to see how these respond to like the notion of modal analysis being that we can obtain the natural frequencies and the mode shapes of certain structures in certain environments, whether they be free modal analysis with no restrictions or simply restricted by however many restrictions you want to include. So let's go to one step of my workflow, which was creating sort of a step-based thickening of the lattice structure. So just going back to Dr. Sharma's paper here, one of the steps that, one of the ideas that he showed in this paper was that you can use a step-based lattice structure, and that yields a really good absorption coefficient. We can see that in this part of the paper here, where we can see really high absorption coefficients for the step-based gradient. So we're going to try to replicate that. And the way we're going to replicate that is I created sort of a workflow where you can input the scale of your lattice, the rotation of your lattice structure, the unit cell, the relative densities that you want associated with each step. And in this case, we're going to just work with a cylindric model, sort of going with the idea, the notion that we're going to use this as a test model within a lab. However, this being a reusable workflow, we can just go back to that relative density block that we created before and edit certain components within it such that we can use it for different models. So a different cylinder radius and a different cylindric height. And we'll explore this modal analysis after I walk you through the output of that. So now we got the relative densities, filtered out any values which didn't yield certain numbers. So in this case, I just want 3 different steps. I could expand this to include 8 different steps. As you can see here, I can go 9, 10, as many as I want, but we'll just cap it off at 3. So the first step will have a relative density of 0.15, however big that cylinder is. We specified this to be 6.5 or 6.25 millimeters in height, then the radius being 12.5 millimeters. So we'll do that for the relative density filter. Then for each lattice, we created our lattice structures as we used in that custom block before. And we can see here that it just looks like one lattice. And what are we going to do with this? Because this doesn't really like give us our final solution. The reason being is that the 2 other lattices that we created are actually hidden within this thickened lattice structure. So we created 3 lattices, however, they're not stacked up on top of each other as we would like. So what I did was used basically a translate object block so that we could actually translate the 3 lattice structures such that we could get basically all the lattice structures stacked. And you can see here that the thickness of the lattice structures change as we go down. So we can see it relative density of where we say 0.15 here, then 0.25, then 0.35. And from there, just to make it a more robust model for us to use in a lab or a test setup, we created like a bottom plate for printing. Then we Booleaned everything together, and we were able to get our lattice structure. So you can see the 3 lattice structures stacked up on top of each other and a bottom plate, and then just create like a mesh from that, as you can see here. So now we have this lattice structure, and let's say we want to assess the mode shapes and the natural frequencies. And this is something new we're going to explore in nTop right now. This idea is not really a new concept. This block has been within nTop platform for as long as I can remember, but we haven't really explored it in an nTop live video. So I'll walk you through this. Basically, we have our lattice structure, and we want to do sort of a modal analysis with it. We want to get our natural frequencies, our eigenfrequencies. How can we do that? So using modal analysis in nTop is pretty straightforward if you were to work with lattice beams and lattice structures. You can get your results very fast and very efficiently. So what we can do here is to basically use this idea of lattice meshes and lattice or this like beam elements to our advantage. In the case that we can use or we can create from the lattice structure that we initially had. So we have our 3 lattice structures. We rearranged it using that same logic that we used before. We have our 3 lattices stacked upon top of each other. And we can create an FE lattice mesh out of this. From here, we're going to thicken the lattices. And in this case, you realize we're not actually using relative densities. And the reason being is we can actually extract the information of the strut diameters. So we input this idea of relative densities, and then we can actually extract the information of the strut diameters from that and assign the strut diameters that we got from that initial like relative density value to each of these lattice structures that we have here. So we thicken the lattice structures here. Then we created an FE model. And if you look at previous videos on simulation techniques, this is one of the most important steps, is just assigning your components, assigning the material, as well as creating whatever tie constraints or connectors that you need. So in this case, I created an FE lattice component, assigned it a material, and you can see all these variables here. So we can assign it like whatever material we want. So if we scroll all the way to the top, I assigned this to be like a Young's modulus, my Poisson's ratio, and my density value. So in this case, I believe this is AL6061 that I assigned it to be. So chose those values, assigned some tie constraints. We really need some tie constraints since we use this lattice structure that we created, which is the unthickened lattice structure from the original model. However, we needed to tie basically all of these lattices together. And how we did that was basically operate through a list, so we could see what lattice structure was close to like the next element in that list and essentially create our tie constraints that way. So we saw the intersecting tie constraints, as you can see here, through the yellow dots connecting each lattice. And we need that to all connect together so it forms obviously one full model. And then finally, we ran our modal analysis. And you can see here, like we can work through. So you can see that the first 7 or 8 natural frequencies are what I'd say to be basically like negligible, since we're working with a free modal analysis, as you can see here. So there are no restraints applied. Assigned, I believe, 20 nodes to this model, and just create our FE model from this. And we can explore like the deformations and the mode shapes for each lattice structure through this. So we can go through different frequencies, see how the structure operates, see these cool sort of deformations. these animations, you could say. We can see like the displacements. It's very cool. And obviously taking a look at the heat map. So how can this really benefit us? Basically, we have all these natural frequencies you can see here. Let's say 20 kilohertz, 23 kilohertz, 24 kilohertz, and so on. And say we go back to this, this paper, scroll all the way to the top, and we see that like each of these components will encounter a certain frequency when it goes through turbulent environments or turbulent conditions. This could be in an aircraft, this could be in a combustion engine for a vehicle, and many other applications. And if we were to encounter frequencies which are equivalent to the natural frequencies that we encounter within the simulation, that could be a cause for concern, since we might not want to encounter these sort of frequencies such that our model like encounters like these sort of mode shapes or these deformations or displacements. This is similar to the notion of having like a building, and you want to avoid basically building a structure which meets the natural frequency of, say, an earthquake, which has that sort of harmonic oscillation to it. So in that similar respect, we can apply this to automotive and aerospace applications. So you can do that here. So we see that step gradient. We can see the difference in the thickness. So we see that difference in the thickness in the first and the top section, in the middle section, and the bottom section too. You can see the difference in the strut diameters if I scroll in a bit more. So now, we did this with a step-based thickening. What if we were to do this with ramp-based? So if you go back to the paper again, we can see that in one of the subsequent sections, we had this sort of ramp-based grading. So nTop, as you might know, works really well with ramp-based thickening strategies or ramp-based grading strategies. And pull up this model, very similar model, very similar structure. You're all going to get these files when we post it. However, it's a similar setup. In this case, we're specifying a relative initial density and a relative final density. And we can also specify a ramp continuity. You can go with geometric, tangent, or curvature. So geometric is basically a linear ramp. Curvature is sort of that exponential ramp. So we can specify our cylinder radius, cylinder height, and all these parameters for our modal simulation. And in the end, in this case, what do we say? We specified an initial relative density of 0.1, final relative density of 0.4. Our scaling factors as such, and you can see that as you go down from the top of this test model, which we include in like an impedance tube setup, we can see that the thickness of the lattice structure increases as we go down. We'll scroll in for that again. So you can see the thickness increase. And similar to the setup for the step-based gradient lattice structure, we can see in our FE model, we have our thickened lattice structure, and then we applied our modal analysis. You can see that cool sort of animation again, seeing that how that works. We'll go to a different frequency and we'll see the mode shapes. It's cool to check out. And why am I using this FE lattice mesh? Why don't I use, we have like an FE solid mesh which you can use. Why don't I basically use that, like the FE mesh or FE volume mesh in this case? Reason being that using simply an FE lattice mesh can really improve or expand, improve like the processing time, since we're just working with beam elements in this case. So it's much smoother and much faster to use like a modal analysis or run a simulation with beam elements versus a solid mesh with the TED elements that you'd create. So if you encounter a structure where you simply have lattice elements and you can optimize it such that you just run the simulation on your lattice elements, I strongly advise you to use this idea of FE lattice mesh since it really improves your workflow. regardless if you're using modal simulation or if you're actually doing like a structural based simulation or buckling simulation for all that matters. So we have this, and say that we're actually doing a study in the lab and we want to get like, I don't know, we want to repeat this workflow for numerous different lattice structures. We just don't want to do it on like one of these, and we don't want to keep typing in like a different relative density, a different scaling value, a different rotation. We want to get our eigenfrequencies for each of those models out, but we don't want to keep doing this in nTop. It'll get tiring, take up a lot of your time. So how can we like automate this? How can we passively run this workflow? So one of my colleagues, Deho, created has been working on this idea of integrating our product with nTop CL such that we can run a design of experiments, or DOE, through Python, through Mode Frontier, or just through the simple nTop command line or MATLAB or any of those programs. So in this case, I created a Python script which you can just input various values of whatever relative densities, whatever scales to your like lattice structures, and you can export basically a mesh file of all the different lattice structures and the associated eigenfrequencies, or the natural frequencies with each of those lattice structures. So the reason why I set up like the all of my files using this like these basically parameters in my notebook is such that we can actually go into our Python script and assign values to all of those values or parameters within my notebook. And I'm not going to explore too deep into the Python script which I created. Again, this will be shared with all of you. But essentially creating this design of experiments where we can assign like a list to each of these parameters of different values we want to go through. I'm going to go through like 3 or 4 step gradients. In this case, this will be applied to the step file, different volumetric types associated with this dictionary of values, different initial relative densities, average relative densities, and basically creating our file directories where we can export all these files. And if you go through what Deho, can see this here, in our support side, we have some information on how to create like Python scripts and connect this to our command line and essentially create that DOE workflow. And I just want to point you to, thanks to an individual by the name of Dr. Sarkar, we essentially use this library to create this sort of DOE setup that we have here, or creating all these like samples from each of these parameters that we specified here. And we're able to create, like, you can go through like a full factorial. If you actually go into the nitty gritty of how DOEs work, you can do a half factorial sort of DOE where you don't take in all the parameters, but you only take in select parameters such that you don't have to run your experiment like hundreds or however many times based upon the number of parameters that you input. We can share that link with you. It's a pretty solid GitHub repo which goes through all of that. So finally, if you run this, you'll get like sort of an output. We can see here, if we go to the File Explorer, we can see some output mesh files. Let's check out one of the ramp gradient ones. We'll check out this file. And it'll just be a simple mesh file consisting of the lattice structure, and we can get this ready to print. And if we run this passively, then it's much smoother. Like, we'll get all these mesh files and then we can just print them on whatever 3D printer that we choose. And at the same time for each of these, so in this case, I labeled it by a certain like unit cell size, the rotation, the initial relative density, final relative density for this ramp structure. And we're able to get our eigenfrequencies just as a list. So we can see like the initial eigenfrequencies as well as the eigenfrequencies down here associated with the modal analysis. And this would be for just a geometric lattice structure. So this will run, we can do it for step-based gradient. And as I said, it just really improves the efficiency since I can just run this passively and my computer will just churn out all the different meshes and all the different different lattice cell types and their associated eigenfrequencies when it runs the modal analysis through nTop CL. So you see that running here. And these files will not be affected when I run through that. So just as a recap, what did I basically walk you through? I walked you through three really important ideas. This idea of reusable workflows, creating that sort of reusable workflow that, for example, my colleague Ryan O'Hara created through this notion of relative density was really helpful. We don't really need to thicken lattice structures. A more robust way of actually thickening your lattice structures for certain designs is to really use this idea or use this notion of relative density. Second idea being modal analysis. How does modal analysis really benefit you? We showed you an example of how modal analysis can help you in aerospace and automotive applications. And this can be directly attributed to sound absorption. So we saw through that paper that Dr. Sharma created was sound absorption is certainly interesting attribute, and we can take this sort of analysis further and basically set this up such that we can do a sound absorption study. However, the modal analysis really gives you this notion of what the natural frequencies of the part are, and basically how we can redesign this part such that we can thicken in certain regions, we can reduce the thickness of certain strut diameters, reduce the relative densities, such that we avoid certain natural frequencies when these components are actually attached to aerospace or automotive applications. And finally, setting this up as a DOE in Python so we can repeat the simulation passively. And those are the main three advantages that say running simulations passively, having this idea to integrate all the designs and simulations together, and this notion of reusable workflows. So the files will be attached for you to check out. You should also take a look at the support site, support.ntopology.com, where we go through this idea of nTop CL, how we can work with Python scripts and such. And I'm sure we're going to create more videos in the future on this idea of modal analysis. I'm sure it's very helpful for everyone using these automotive and aerospace applications. And with that, thank you very much for watching.